Welcome to a new test and teardown video. This time it's a DC power supply, but it's not just a normal power supply. Oh no, it's a dual auto-ranging power supply from a company called Radiofon. And this one is built like a true dual mono kind of design. 2 units completely independent. They even got separate mains switches. This one is falling apart. And it turns out, I didn't know, but Radiofon is a Danish company from Slangerup. It's written on the circuit boards. But I cannot Google anything at all about the company or the power supply or anything like that. So of course this one is old, and I think it's from about 1970 to 1980, something like that. So let's look inside this unit and see exactly what I mean about the dual mono. It's a term from audio amplifiers, as you can of course imagine, but they are just 2 completely isolated systems, and they only share mains entry cable, so there's only one mains entry, but other than that it's 2 completely isolated units. And I think for service friendly design it's quite alright. We got 2 circuit boards in sockets, so you just pull these up, and the auto ranging system is made like this. So this is the rectifier board and a relay and 2 transistors and some resistors and stuff. I believe this measures the voltage across the output series regulator transistor, and when this voltage is too little, it will pull the relay and make the voltage higher. I cleaned the circuit boards here, so they're really nice and shiny. They were full of all sorts of old dirt. I used acetone to clean these because it just didn't work with alcohol. And see here on the text it says Radiofon Electronic, and then the postal code is 3550, and then Slangerup, that will be the city of the company. And see, this circuit here is not using any other signals than the voltage here, and then it pulls the relay. That will be the center of the relay. So that's just what it's doing. I've been looking a little bit on this relay. Maybe I can get a picture of that. I don't know if this is visible here on this picture, but there is a little tin whisker or something like that between the contacts out here. If you look really careful, I should probably remove the plastic cover, because this relay cannot be working good. Also, if I take my ohm meter, I can actually measure some sort of a connectivity between those pins. And the fun thing is, when I reverse my ohm meter, I get different results. So this is because those tin whiskers, they act like diodes, because they are insanely thin, pointy needles into a piece of metal, and that ends up acting as a diode. I think that is a little bit funny. So that will be the rectifier board, and the transformer here is also a little bit funny. We got 3 voltages output, 2 times 18, that will be the main output voltage. I think that will be the voltages that goes via the relay. And then we have a 6.3 volt, that is an auxiliary voltage for the reference and voltage drive and all that kind of stuff. And 46 is not used. So that is the last one here. So that is some sort of a weird transformer to use for this with this one extra winding they're not using. And also on the primary side, we have 2 times 110 and then a 20 volt winding. So that means you can make 220 plus 20, that is 240. And this is what we need to do actually. We should move this wire to this point because today we are closer to 240. And like 20 years ago, we used 220. So that is the thing. So I wanted to adjust this as well. And then there's another little funny thing. The heat sinks. We got an output power transistor TO3 style here, big one. And then we have a driver, a local driver. So we have only 3 wires going to this point. So this is of course the unregulated voltage with full of ripple, and this will be the output voltage. And then for good thermal, the transistor here is not electrically isolated, so there's positive voltage on the heatsink, and that is why the heatsink is isolated from the chassis. And you see those isolations, they are breaking up there, there's plastic cracks, and we also found a few of these plastic parts inside the cabinet. So this seems to be a problem, and we also have a little bit of isolation issues here, not super perfect. And yeah, what else can I see about that? The fuse here, this is a classic problem with those fuses. They tend to corrode, and when I try to measure this fuse, I get very different results depending on how I touch the socket here. So I think I will take this apart and clean this a little bit. That will be the current sense resistor. See, output, it goes via this resistor into the output. So this is the regulator board. Quite nice, and it says of course 771. Probably the 2 here is for dual or something like that. Maybe they're using this regulator board for all their other power supply units or something like that. It also looks like we could put in different IC types in this footprint. Let's look a little bit on the regulator IC. That will be the RC723. And it's super easy to find a data sheet of this 723. It is probably the most used, most famous IC for DC power supplies. It contains of a super good reference, a voltage reference, and an op amp and a power output. It can do current limiting and yeah, all that kind of stuff. And it's super accurate and stable and all that. So that is definitely what they're using here. And I found a schematic on the internet that was more or less looking like the power supply I got here, just for easy measures to show you a little bit of about what the regulation board is doing. Let's look a little bit more about the rectifier board, what that one is doing, because at first glance it was looking quite simple. We got only 4 diodes, and then of course the relay, and then that capacitor here, and that goes to the output stage and all that kind of stuff. So I made a nice little schematic here to explain what is going on. The fun thing is the wires. So we've got the black is center, and then green and green. And that is a little bit confusing. I don't know if we can get enough light to show you the colors. But see, green, green, and then black. You would definitely think the center one here. No, it's here. That's weird. I had to measure this to verify what is going on, because it didn't make any sense. when I wanted to make a nice little schematic. So the idea is the two green AC, they drive the bridge, and in non-energized mode, the relay is connected like this. So the bridge drives the capacitor with full voltage. So if you want half the voltage, you have to energize the relay, then it flips over here. And now it's the center of the transformer that goes to the positive of the capacitor, and then the negative side is, now it's not a full bridge, but it uses this diode or that diode to half of the transformer, like that, right? This one, that one. So that is quite smart. They can, it's still 100 Hertz, obviously, as you can see here, but it's either all four or only two of them, and it's half the voltage or full the voltage, and you're only using one simple change over switch like that. And now let's look a little bit on the main switches. This one is of course completely broken. See, there's no way I can repair this because the plastic is cracked like that, and obviously all this stuff fell out. And this is the one with a little neon bulb inside, and I kind of like them with neon bulbs. So I went through my stock, and look what I find. I mean, this one is, it's a little bit more tough compared to these. Quite nice, but from a distance, I mean, can you see the difference from a distance? I don't know. So I think I can restore this, and that is what I want to try and do. So let's try a little first power up. Here I want to show the output voltage and the capacitor voltage at the same time, and then we're going to play around with output voltage adjustments and see what happens. I don't want to play with the right supply yet, because I just want to focus on one of them first. Okay, so mains applied, and then okay, it's using 2.7 watts, and we got negative a half a volt. And we got, okay, we got output. So that was the current limits. So current limit goes to 0. Oh, did you hear that? We got the clickety clickety. So at low output voltage, we only got 27 volts on the capacitor. So let's try and dial up output voltage and see when it happens. Click. Oi, 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 oi. Then it goes to 50. And click, and then it discharges, of course, to 27. So that is, whoa, that is a lot. Is that really necessary? So from 0 to, okay, 12 point something. Then it clicks to 55. I would say it is a little bit high. So it's, this design really wants to make the heatsink warm, right? And then we can of course continue all the way up, and this is, look at that, and then it goes really, really slow. Is this normal? What? It can go quite fast. Down to 20. Okay, and then up again. Okay, so there's There's a nice hysteresis on the relay. Well, it sort of works, right? So I was about to assemble the right power supply as well. And of course I double check the switch here. And there's a loose connection. How annoying is this? I was so close to click this in. No, I am so happy I didn't do that. Hey, I'm not giving up the first try. I have nothing to lose really, because this switch we already confirmed is not working. So I took it completely apart, and I was able to take a screwdriver in on each side here and then gently wiggle this part out so I could get it out. And it's of course those tabs here at each side here that clicks in. So this is I think everything here is more or less symmetric. There is this little thing here where the lamp is, and this is in one of the sides. So it does matter how I assemble this. And this is why I added a tiny little dot, as you can see here. I also added a tiny little dot right there, almost invisible. And then I added a tiny little dot right there. I'll clean these off later, but I want to try and see if I can figure out why this is not working. So that will be the contacts. I didn't clean anything yet, but you can see it's quite dirty right there. And they go in here like that. So that will be the contact point up there, and the other part just kind of rolls around this piece of metal. So the idea is they go in like that, right? And then this springy part can go up and down, and it sort of slides right there. So if I take something that can slide a little bit, and it goes like flippity flappity right there and creates the contact when it goes this way. And now it's off and then it's on, as you can imagine. But you can see here it's quite dirty and nasty right there. And this rolling part here is what creates a contact for the lamp. So we got this little piece right here that can move up and down, and then it touches a little spring. They're supposed to be able to move, and there's supposed to be a little spring in here. And maybe that is something I need to take apart and clean and see if I can get this to contact better as well. This way the lamp will also work. See, this is the new one with a nice clean lamp. And if we compare this with the old one that was broken, look at that lamp. It has been running a million hours, and everything here is all yellow and nasty. I found out exactly why this switch is not working. And I think if I share this with you, you will be able to repair this type of switch. Look at that. These two little metal parts here, they're supposed to be able to move in and out nice and freely. See, if I push it, see, it's not coming out. And this is why it's not working. See, it's coming slowly. And this slowly is, of course, causing the contact part that moves to arc and create bad connections. We need to have a fast and stable and strong push force, and then it will work. So I'll try and see if I can just clean this. I think it is just old lubrication that turns itself into chewing gum. So I'm quite happy about this unit now and this repair. See, now the switch is working, and of course the location of the bulb is a little bit different compared to the bulb like that. There was nothing I could do about that, but I mean, it sort of works, right? And see, nice and stable, no loose connections or anything like that. So let me show you I adjusted this a few hours ago. It's just keep the voltage insanely accurate. And that is, of course, this chip is just fantastic. So let's try something funny. I cranked up the current, and this is 0 amps, and let's just give it 2 amps. And of course I'm pulling the current here, and I'm measuring here as well, so you can't really take this for anything, and there isn't any sense on those banana plugs right there, so but it still works, right? And then we go to AC, and I am not able to measure any ripple at all. So whatever they have done, it's definitely working quite well. And also, 2 amps. So let's turn this off. So 2 amps and 10 volts. That is 20 watts of output power, right? The input power is 56. So it's not that bad. And of course, if I crank up the volume, listen. Here we go, clickety click, right there. So that's 13 volts and 2 amps. That is what, 26. Measuring 26 at my load at the moment. Now what do you think is going to happen? Here you go, 110 watts. And that is, of course, due to the very high voltage on that capacitor right now. So there's only a few tiny little things I want to show you. Remember earlier in the video I talked about the heat sinks being isolated from the chassis, and the original nylon plastic holder thingies, they're like completely cracked, and it was really bad. Over here we only had 2 of them left, and as you can see here, I 3D printed some new little things, and they're just this little piece here, and I use 2. Of course I made it so that they also make sure there is a distance from the heatsink to that part of the chassis, and the parts that goes in between here are just glued using contact glue, and then stick in the screws, and then this little part there makes sure there's nice isolation. And this is PETG, so it handles quite a high temperature, so that should be fine. And I also want to change these over here, so this power supply is now in tip-top shape again. I don't know if I showed you the bottom part of the power supply. It had completely dissolved feeds. So of course, while I was at it 3D printing, why not make some new feeds for it? So now all is perfectly fine, and I can reach down here with my fingers and lift it up. And you can see the completely dissolved feed didn't give it any height here, so it created a little bit of damage to the mains cable. And you don't see any air venting holes here on the back, and that is a little bit sad, because this type of heatsink here would really benefit big time from holes in this area here on the bottom and on the top as well. Now it's only half of the heatsink that sort of works. How much air is going in and out here? I mean, you can tell that it's not all designers that spend a lot of time thinking about optimal thermal design, but I kind of work with optimal thermal design for a living, so I can just see this from a big distance that something here is completely wrong. Yeah, well. Or what you could have done, take the heatsink and put it outside. But that will of course make the case a lot bigger. Then the case could have been made smaller and then put the heatsink outside. I don't know. You can decide what you want to do when you design something, but That's the kind of things I would have argued in this design, at least. Anyways, I want to say thank you very much for watching. It has been a lot of fun repairing this old power supply. Bye bye.